Today's lesson is Chapter 2, Section 1 of Algebra, Write, Solve, and Graph Linear Inequalities. Now, this is our first unit on this topic, and then we'll get progressively more challenging as we go on. So today we're just starting with the basics. What are these inequalities? Hopefully this is a little bit of review. We have less than, greater than, less than or equal to, and greater than or equal to. And our challenge today is primarily going to be focused around graphing and making sure we can do this accurately. If we look at the words x is less than 2, it goes with a symbol x is less than 2. We still read it the same way. But graphically, we're going to shade on a number line all of the numbers that are less than 2. Now 2 does not count as being less than 2. So notice the dot at 2 is hollow, and then we shade all of the numbers to the left that are less than 2. The next one, x is greater than 2. Similarly, it cannot be equal to, so we use a hollow dot at the number 2 and shade all of the numbers that are more than 2. So starting at 2.000001 and off to the right. Our other two, less than or equal to or greater than or equal to, in this case, it can equal that boundary number. So on the graph, we represent that by a solid dot at 2. And for x is less than or equal to, then we shade to the left. For greater than or equal to, we use a solid dot and shade to the right. Let's look at some examples. First, write the sentence as an inequality. It says a number b is fewer than 30.4. Fewer than is very much like less than, and we need to decide, is this less than or is this less than or equal to? So I'm going to write b, and in this case, if b has to be fewer than 30.4, it cannot be equal to, so I simply write less than 30.4. Our next example, number 2, we have negative 7/10 is at least twice a number k minus 4. This one gets a little more complicated. That is at least is our inequality part. So let's start with a negative 7/10. That's just going to stay the fraction, negative 7/10. Is at least tells us that it's going to be greater than, or because it's at least, it could be equal to. So our symbol, greater than or equal to. And then finally, we have to interpret twice a number k minus 4. Twice a number means 2 times. K will be our variable, and then minus 4. And in today's lesson, our challenge is simply to write the inequality. We don't actually have to solve it at this point. Examples 3 through 6, our directions are just to tell whether negative 6 is a solution of an inequality. Well, we can determine if a solution is a solution of an inequality just like we can with equations. All we have to do is substitute that value for the variable and decide if we get a true statement or false statement. If it makes the inequality true, it is a solution, and if it does not make the inequality true, it is not a solution. So first I'm going to plug in negative 6 for C. Plus 4 is less than negative 1, and we need to decide if this is true. So I'll simplify. Negative 6 plus 4 is negative 2, and that is less than negative 1. So yes, negative 6 is a solution. Number 4, 10 is less than or equal to 3 minus m. I'll rewrite this inequality with our value negative 6. 3 minus negative 6 is equivalent to 3 plus 6. 10 is less than or equal to 3 plus 6 is 9. This is false. So negative 6 is not a solution. Problem number 5. 21 divided by x is greater than or equal to negative 3.5. 21 divided by negative 6 is greater than or equal to negative 3.5. 21 divided by 6. 6 doesn't go into 21 evenly. It goes in 3 times to make 18 with a remainder of 3. So it's negative 3 and 3/6, or negative 3.5, which is not greater than, but it is equal to negative 3.5. And again, we can say, yes, negative 6 is a solution. Number 4, 4x minus 25 is greater than 2. 4 times negative 6 minus 25 is greater than negative 2. 4 times negative 6 is negative 24. Minus 25 is greater than negative 2. This doesn't look very true because negative 24 minus 25 is negative 49. And that is definitely less than negative 2, not greater than. So this, we can say, not a solution. Let's look at a few examples where we need to graph. Problem number 7, we have to graph b is greater than negative 8. We're going to start with just a regular old number line. One thing that I like included in every number line is that reference point 0. In this case, because I'm looking at numbers greater than negative 8, I need to include 0 and negative 8. I'll put 0 all the way over on my right, and then count down. 1, 2, 3, negative 5, 1, 2, 3, 8. It's very important that we label this point at negative 8. Now, to do the graph, I'm going to use a hollow dot because it cannot be equal to. Negative 8 is not a solution here, but everything greater than negative 8 is. So I shade to the right and make an arrow to the right saying everything in that direction would make this equation or inequality true. Problem number 8. 1.4 is greater than or equal to g. Again, I'll start with my number line. This time I'm going to put 0 on the left because I'm looking at the positive side. And I'm going to go by 2/10 per tick mark. So if I go 1, 2, 3, 4, 5, that's going to be 1. That's going to be 2. And that should be enough. 1.4, I need to label it. Since my tick marks are 2/10 each, 1.4 will be this one. Because it can equal g, I'm going to use the solid dot at 1.4. And it says 1.4 is greater than g. One common mistake I see in graphing inequalities is that if they see this greater than sign, they just automatically shade to the right. And that's not the case, like it was in number 7. In this case, we're saying 1.4 is bigger than our variable, so that implies that our variable is less than or equal to 1.4. So the numbers that 1.4 are bigger than are like 1, 0.6, 0, and those are the solutions. So in fact, I shade to the left for this graph. Number 9 is a little awkward. We need to simplify this first. It tells us v is greater than or equal to the square root of 36, which is equivalent to saying v is greater than or equal to 6. We'll graph this on our number line. I'll start with 0 on my left and start counting. V is greater than 6. or equal to. We'll use a solid dot at 6, and then shade to the right. The numbers greater than 6 are 7, 8, 9, 10, and going on forever. Finally, let's see when we can use this in real life. This graph shows the height restrictions h in inches for 2 rides at an amusement park. We're asked to write an inequality that represents the height of each ride. Ride A gives us this graph. We have a solid dot at 48, shaded to the right. So for ride A, our height is being compared to 48. And notice it's all the numbers greater than 48. So is greater than or equal to, because of the solid dot at 48. There's our inequality for ride A. If we wanted to represent this using math notation for ride B, again, we're still talking about height, so I'll use h. But this time we have a hollow dot at 52 and we're shaded to the left. These are all the numbers that are less than, but not equal to 52. So I just use a less than sign and 52. It would be nice to label these with units. Both of these are being measured in inches. And that's our introduction on inequalities.